Now we want to actually use these multi-objective optimization for a problem of higher moments portfolio optimization. So we need to write some codes in order to solve this optimization problem where we have mean, we have variance, volatility, we have skewness, which is the third order moment, and finally we have kurtosis. So we want to maximize mean and maximize skewness, and we want to minimize volatility, and we want to minimize kurtosis. So we can handle this problem in two ways. The first approach is the naive approach, because in general you have hundreds of assets, you want your precision to be high, you want to solve the problem as quick as possible, so you cannot use discrete problems. So, but we use it here because traditionally it has been solved by extended Jahn-Graef-Younes algorithm. But you cannot scale it. In general, your problem could be very complex in terms of curse of dimensionality, order of complexity, or these things that we use in computer science or even in statistics. That's why we just talk about it, discrete case, but we don't use it very much. We use it in the initialization maybe, but not for all problems. And you can solve this discrete problem very easily. It's like using an ordered list, and from left you try to do forward iteration, and from left you try to do backward iteration, and finally you cover all of the points, non-dominated points. So as I said, the new set U is built by going through the original set, because here we assume that A is finite. So we have finite points in our objective space, maybe 120. I don't know, maybe 1000. But it is finite, and it is not very much, because you want to do it manually. You want to check all of the points to see if they belong to the non-dominated sets. So we construct it like this. We go through the set from beginning to end, and by comparing each element only with elements considered so far, which have not been turned out to be dominated. This is the forward iteration. And in the second approach, second loop, which is which is backward iteration, we have a set T. The new set T is built similarly, but this time by going through the set U and by starting from last element. In the forward, we go from first element to last element. Now we go from last element to first element. So for all elements in the set, finally, complete comparison with all other elements of the set A has to be done in a final loop. So if this is the set D, U, and T, the discrete problem for minimal points is similar as well. It has 3 parts as well. First, in algorithm 1, we do it for non-dominated elements. In algorithm 2, we use the same analogy to do it for minimal elements as well. And for continuous problems, which are interested because many real problems could only be solved using, they can only be solved by continuous approach to multi-objective optimization. So before saying that what we are doing, I should say any non-dominated element with respect to D is also an efficient element of A with respect to Y. And if K is an intersection of all those cones, then the second part says that any minimal element is also an efficient element. So using this lemma, this is the functional that Gershwitz functional that Christian Temer used to work on, but it is not the only functional that you could use. So the set of efficient element with respect to K is epsilon K, which is a superset. So if this is epsilon K, it is the superset of the set of non-dominated and minimal elements. So minimal elements and non-dominated are here. So we want to reduce it because it's too big. And we denote the finite set of approximation. So we go from A to C and then T. So the algorithm is very easy. So we prove that if N is constructed like this, we calculate N here. At each iteration, we try to add one more non-dominated element, and finally, we collect all of them. So the theorem says that if N is the set that I just talked about it, then N is a subset of A, and any element of N is a weakly non-dominated element of A with respect to D. So we use theorem 5.11, this one, to prove this. And this is all about what we talked about it, that we need to minimize the functional and evaluate it. If we evaluate it at a non-dominated, at y bar, if it is 0, then y bar is a non-dominated point. And that's why in this algorithm, we say if at line 6, we say that if t bar is equal to 0, in order to satisfy the theorem, if t bar is equal to 0, so if this one is 0, then we can add to our sets, to our non-dominated sets. Then it is one of our non-dominated sets. Because, we have many directions. For example, this is the reference, and we go in direction R, and we have many other points as well. So if the minimum of all of them is t is equal to 0, if it happens that for any y that we start, for example, y here, if it happens that y is here and we don't need to go anymore, then this is the non-dominated points, and we add such points to our n. That's why we are trying to find those non-dominated elements from a zoo of elements that are not useful. And diversity is automatically satisfied. The equidistance between all of them. You see how nice the entropy is? We are not just finding a simple cluster, but we are also trying to find the diversity. So not only your accuracy of algorithm is important, not only it is important for you to get closer to your efficient frontier, but also you need to know that you need diversity as well, diversity of the solutions. You want to find all of them. You don't want to just concentrate in a special single cluster, but you want to discover all of these clusters as well. And also you can also use use the same analogy for finding minimal elements. Everything is the same. N is replaced by M because it's a minimal elements, not non-dominated elements, and everything is the same.